This video will cover Chapter 12 on relationships between two categorical variables and the chi-square test. We'll talk about formulating hypotheses in order to test a relationship between categorical variables. We'll look at performing the test based on both proportions and on counts. We'll introduce the chi-square test and talk about the relationship to confidence intervals. Additionally, we'll look at framing the hypotheses as questions about both variables and parameters. We'll talk about how to compute the chi-square statistic. We'll look some more at the details of the chi-square test and how to handle confounding variables. In the 4 stages of statistics, we're talking about statistical inference between two categorical variables. So remember that we can state the null and alternate hypotheses about variables, whether they are related or not. We can also state it in terms of parameters, whether something is equal. For a relationship between categorical variables, we're asking whether the population proportions are equal. So let's say that we're looking at whether smoking plays a role in alcoholism. How do we formulate the null and alternate hypotheses? In terms of variables and in terms of parameters. In terms of variables, the way to formulate the null hypothesis would be to say there is no relationship between smoking and alcoholism. The alternate then would be that there is a relationship between smoking and alcoholism. In terms of parameters, we would say that the proportion of alcoholics in the population would be equal for both smokers and for non-smokers. That's the null hypothesis. The alternate would be that the population proportions of alcoholics are not equal for smokers and non-smokers. Notice that the word not appears in the null hypothesis when we're talking about variables, and it appears in the alternate hypothesis when we're talking about parameters. We're going to focus on parameters, but before we go forward, one more thing about this. Here, because we're looking at two categorical variables, we're breaking the population down into two groups in two ways. We have alcoholic or not, and we have smokers or not. So here, when we're talking about the population proportions, we're first breaking our population down into two groups. In this case, the smokers and the non-smokers, and then looking at the proportions of alcoholics within each of those subgroups. It's those proportions that we're saying are equal or are not equal. So, does smoking play a role in alcoholism? Here's a hypothetical table of data that's collected about this question. What should we look at here in order to answer the question? Again, we want to compare the proportions of alcoholics for both smokers and non-smokers. Notice that we're breaking the population down in terms of the explanatory variable first, smokers and non-smokers, and then within those groups, looking at the proportions who are alcoholic. P1 hat is 30 out of 230. Notice that's a conditional proportion. It's 0.13. Within the second group, P2 hat is 0.013, 10 over 770. That seems like a pretty big difference. So looking at these two sample proportions, where would we go from here? Can we focus on this difference between the sample proportions, 0.13 minus 0.013? Well, sure, we can actually standardize this. We're looking at just a relationship between two proportions. We've got a pretty big sample size. So the difference in proportions is normal. We've seen this before. We can compute z. It's the difference between the two divided by the square root of something. But this is where things start to get sticky. We can use z to test against a one-sided alternative. For the other test that we're going to talk about, the chi-square test, we cannot. The disadvantage, though, and this is a big one, is we can only do this for a 2x2 table. If there are more than 2 options in each category, things get more complicated very quickly. There's not just one difference to look at. You got P1 hat minus P2 hat, P1 hat minus P3 hat, P2 hat minus P3 hat, etc., etc., etc. That's just too much. Instead of looking at proportions, though, we can also look at counts. We've talked about how to create a table of expected counts before. Remember the WASP study? We took our observed counts and created a corresponding table of expected counts. Do you remember how to do that? So let's look at this in terms of counts. To test the null hypothesis, which is that the proportions are equal, we'll look at a table of expected counts. So here's our data on smoking and alcoholism. If the null hypothesis is true, that means that there's no relationship between the variables. Then, because the overall proportion of alcoholics is 0.04, we would expect that same proportion to hold in each of the subgroups. So for the smoking group, we would also expect 4%, or 9.2, to be alcoholic. And in the non-smoking group, we would expect 4% of the 770, that's 30.8, to be alcoholic. Similarly, 960 out of 1,000, that's 96%, are non-alcoholic in the population, so that same proportion of the smokers and that same proportion of the non-smokers should also be not alcoholic. So here are the expected values within each of the 4 possible subgroups. Where do they go in our table of expected counts? Well, that 9.2 is both smokers and alcoholics, so that's going to go in the smoker row and alcoholic column. The 30.8 is non-smokers and alcoholics. We'll do something similar for the other 2 numbers. Notice that 9.2 out of 230, that's the proportion of alcoholics out of the total within the smokers, is equal to 30.8 divided by 770. That's the proportion of alcoholics in the non-smokers, which is also equal to 40 over 1,000. That's the proportion in the whole population. That's what it means to say this is the table of expected counts. So here it is. Remember that we can compute these quickly and easily by taking, looking at each cell and multiplying the sum of the numbers in the row times the sum of the numbers in that column divided by the total of the totals. So we take the row total times the column total and divide by the total total. That gives us all the numbers that we want. So once we have the expected counts, we're ready to compute our statistic. We call this statistic chi-square. That chi is the Greek letter that looks like an X, and it's squared. That's the way we'll often abbreviate chi-squared. The components of chi-square look at the observed and expected counts and compare them. Once we take the observed and expected values, we'll find the difference and square it, and divide that number by the expected count for that cell. You can think of each of these components as individual standardized squared differences. The standardization comes from dividing by the expected value. It's almost like we're looking at this as a percentage in a way of the expectation. To get chi-square, we just add all the components up. So chi-square is the sum of the standardized squared differences. So here is our smoking and alcoholics example. What's the chi-square statistic? Well, we have 4 cells that we care about, so it will have 4 components. We'll find each of those components and then add them up. For the first component, we subtract observed minus expected, that's 30 minus 9.2. We'll square that result and divide by the expected value. Then we'll add, going to the next cell, the observed of 10 minus the expected of 30.8, all that squared, divided by the expected, which is 30.8. And then we'll move on to the next cell, we do the same thing, and we move on to the next cell and do the same thing. We do all those calculations all put together, and we get 64. So, chi-squared is 64. Now, our question for this, as it has been for everything else, is that big? Well, we don't have enough information to answer that yet. It depends on how the chi-squares are distributed. Well, let's take a look at that distribution. Chi-square distributions, assuming the null hypothesis is true, follows a predictable pattern. It's the chi-square distribution. Just like the T and F distributions, the chi-square distribution has degrees of freedom. It's the number of rows that we're looking at, minus 1, times the number of columns that we're looking at, minus 1. So, if you take R as the number of rows, that's the possible values for the explanatory variable, and C is the number of columns, then the degrees of freedom is R minus 1 times C minus 1. The chi-square distribution is not negative. Notice that all the terms are squared, so there's no way we can get anything negative. The mean of the chi-square distribution is just the number of degrees of freedom. So for a 2 by 2 table, the number of degrees of freedom is 1, and that's the mean of the distribution. For a 5 by 6 table, the number of degrees of freedom would be 4 times 5, that's 20. So the mean of that chi-square would be 20. The spread of the distribution depends on the degrees of freedom. In general, the more degrees of freedom, the more spread. And the chi-square distribution is skewed right, which you might expect since it's non-negative. So let's take a look at a picture. Here is the distribution for 1 degree of freedom. Notice that we've labeled one particular value for chi-square, that's 3.84. That's the critical value for 1 degree of freedom. If chi-square is greater than 3.84, the corresponding p-value must then be less than 0.05. Remember the properties of the distribution, we can see them on display here. It's non-negative. There are no possible negative values for chi-squared. The mean is the number of degrees of freedom. In this case, it's 1. And the spread depends on the degrees of freedom. You can see that the vast majority of the data are within 1 unit of 1. And you can tell that this is very sharply skewed to the right. So, how big was our chi-square of 64? Is there enough evidence of a relationship? Well, remember, our cutoff was 3.84 for 1 degree of freedom. 64 is way bigger than 3.84. So yes, is our p-value small? Holy moly, yes it is. Do we have evidence of a relationship? You bet we do. So, if we only have a 2 by 2 table, remember we can use z, as we talked about before, or we can use chi-square. It turns out they're almost exactly the same. Z squared is equal to chi-squared if we have a 2 by 2 table. So remember, the z statistic gives us a combined two-sided probability of 0.05 for z equals 1.96. Remember, that's also the multiplier for a 95% confidence interval. It's the same number, we obtain it in the same way. What do you get when you square that number? Well, you get 3.84. That's exactly the cutoff that we said earlier for the chi-square distribution. So our chi-square is 64 for that 2 by 2 table looking at smoking and alcoholism. That would correspond to a z-value of 8 because z squared equals chi-squared. So remember, when we're looking at our test statistics, at this point we have z and t and f and chi-squared. What does it mean to be large? Well, remember for z, our cutoff was about 2. For t, it depends on the number of degrees of freedom. It's always bigger than 2, and it can be as big as 3. For really, really small sample sizes, it might even be bigger than that. F depends on all those degrees of freedom that we talked about in the last video. Chi-squared also depends on the number of degrees of freedom, which means it depends on the number of rows and the number of columns in our two-way table. For 1 degree of freedom, that is for a 2 by 2 table, you can kind of keep in mind 4 as being the cutoff for a big value of chi-squared. So remember, for explanatory and response of categorical variables, the roles of each impact what we report. But the roles do not impact chi-squared or the p-value, because remember, we compute the chi-square statistic using the expected values, and the expected values don't care which is explanatory and which is response. We use them both equally. So here, if we're looking at smokers as smokers versus non-smokers as explanatory and alcoholic as response, here's our proportions that we would report, 0.13 and 0.013. But if alcoholism is explanatory, remember the explanatory group is the way that we divide the population first. So we'll divide the group into alcoholics and non-alcoholics, and then report the proportion that smokes within each of those groups. So for the first, it would be 0.75. That's the proportion of alcoholics that smoke. The second would be 0.21. That's the proportion of non-alcoholics who smoke. So here are the numbers that we computed. How can we express the higher risk of alcoholism for smokers and the higher risk of smoking for alcoholics? Notice that our data seem to indicate both of those. Well, we can talk about how many more times likely one is to fall in one group than another. For example, smokers are about 10 times as likely to be alcoholics compared to non-smokers. That's because the top number here is 10 times the bottom number. Now, if we look at alcoholics versus non-alcoholics, what's the relationship between that 0.75 and the 0.21? Well, 0.21 times 3 is about 0.63, times 4 it's about 0.88, so it's somewhere in between 3 and 4 times. So let's talk about our guidelines for chi-square. In order to use the chi-square procedure, our samples need to be random and they need to be taken independently from several populations. We need this for every test that we do. Confounding variables need to be separated out. Again, we needed to do that also in all the last examples that we've looked at. The sample sizes must be large enough to offset non-normality of distributions. We've needed that for everything too. The populations need to be 10 times the sample sizes. That sounds familiar as well. So let's look at these sample sizes. What does it mean to say that the sample size has to be big enough? Here's our rule of thumb. We're going to require the expected counts to all be at least 5 in a 2 by 2 table. In a bigger table, we're going to need to adjust that number. But 5 will work for us in general, and you can use that as a guideline from here on out. Remember, when we've seen this before, these expected values, expected wins and expected losses that we saw back when we were looking at single categorical variables, we required those numbers to be at least 10. Because we're adding up a whole bunch of different things here, we can actually cut that 10 down to 5 when we're doing chi-squared. So remember, the expected counts all must be at least 5. So if we go back to the alcoholism and smoking example, and we cut all of the counts by 10, what's our chi-square? Well, the observed values would be 1/10 as big, so the expected counts are 1/10 as big, which means the chi-square statistic should be 1/10 as big. But we can't evaluate this using the chi-square distribution, because look at those expected counts. The expected counts for alcoholic are 0.92. Hey, you can't see that very well because it's orange. There we go. 0.92, 3.08. Those are both less than 5. Because those are both less than 5, we cannot use the chi-square distribution. So let's look at confidence intervals. Remember, we can use confidence intervals to establish a relationship, or at least get evidence of a relationship, because it tells us how much the explanatory variable affects the response. So if we're looking at proportions, we can either compare confidence intervals for population proportion, or we can set up a confidence interval for the difference between them and look and see if zero's in there. So first, let's look at the two proportions. Let's construct individual confidence intervals for the two groups. So for non-smokers, the 95% confidence interval for population proportion for alcoholics is 0.005 to 0.021. For smokers, it's 0.09 to 0.17. So now if we're looking for evidence of a relationship, what should we look for? Well, if there's a relationship, or if there is no relationship, I should say, the proportion should be equal. But look at those confidence intervals. Are there any numbers that are in common to those confidence intervals? Do they overlap? No, and it's not even close. That means there can't be a common proportion that works for both, which means there must be a relationship. Absolutely. Here's what the confidence intervals look like on this number line. There's the non-smokers way down there on the left, and here's the smokers way up here on the right. They are not close. We can also look at the difference. So the 95% confidence interval for the difference between the population proportions, so that's alcoholics, smokers minus non-smokers, we get 0.088 to 0.146. So what does this say? Well, the entire interval is over here far to the right of 0. If the population proportions were the same, the difference between them, when you subtract, you would get 0. But 0 is not anywhere close to this interval. That means there is a relationship. So let's say that we're looking at the relationship between gender and lens wear. This is coming out of our student survey data. Here are the counts and percentages. So what do you think about the relationship here? Well, I can see that more females wear contacts than males by looking at those proportions. I see that men wear glasses more than women by about a factor of 2. For the none category, they're pretty close. Let's construct our table of expected counts. Remember, to get the table of expected counts for each cell, you multiply the row total times the column total and divide by the total of the totals. So for female contact wearers, that would be 103. For male contact wearers, that would be 60, and so forth, and so forth, and so forth. So now let's take a look at these side by side. Do you see big differences? Well, in some places, especially the first two columns where we noted the differences before. Notice the female contacts at 121 versus the expected value of 103. And we see a big difference in glasses. Those counts were nearly the same in our observation, but they're very different in our expectation. For none, the results were pretty close. It's kind of what we expected. So let's construct the components for the chi-square. Remember, you take the observed minus expected, take that result and square it, and divide by the expected value. We'll do that for each of the 6 cells. Once we have that, we'll add them all up to compute the chi-square statistic. Which of these contribute the most and which contribute the least to the chi-square statistic? Well, it's the largest numbers. Notice they come out of the first 2 columns, kind of like we expected. The ones for the third column are not very big at all, right? So what is chi-square? Well, add those numbers up and we get 18.4. Is that large? Well, remember the mean of the chi-square distribution is equal to the number of degrees of freedom, which is rows minus 1 times columns minus 1. So the mean here is 2. 18.4 seems like it's going to be pretty big. So how many degrees of freedom do we have in this example? Well, remember, it's rows minus 1 times columns minus 1, which gives us 2. Another way to think of degrees of freedom is how many of these you can change before all the others are set. In this case, it's 2, because once we know what those 2, female contacts and female glasses, are, as long as we know what the totals are, I can use that to figure out all the other values of all the other cells. So let's take a look at the chi-square curve with 2 degrees of freedom. The cutoff for 2 degrees of freedom is 6. So if chi-square is above 6, the p-value is less than 0.05. So our chi-square was 18.4. Do we have evidence of a relationship? Well, yeah, because 18.6 is way bigger than 6. So do we get a small p-value? We get a really small p-value. Do we have statistically significant evidence of a relationship? You bet we do. Now remember, we also need to check and make sure that the chi-square distribution is appropriate. We need to make sure that these samples are big enough. And remember, the way to check that is to look at the the expected values. They're all more than 5, so we are good to go. So let's take a look at some software output for a chi-square test. Here the explanatory variable is Botox or placebo. The response is sweating decreased or sweating is not decreased. You can see the row totals and column totals are both 161. So we have expected values that are all actually the same, 80.5. So you see the actual values and the expected values right in the table at the same place. So there, 121 is the observed decreased for Botox. 80.5 is the expected decreased. What can we conclude from this? Well, are the sample sizes big enough? Well, all of the observed values, all of the expected values are bigger than 5, so yeah, we're good. The proportions with reduced sweating are 75% and 25%. Those seem pretty different. And take a look at that p-value. To 3 decimal places, it's 0. So we do have a significant difference. Can we conclude that Botox reduces sweating? Absolutely. Now, next I'm about to show you how to use your calculator and how to use Excel to perform chi-square tests. The data that we're going to use are seen here. I got this from the student survey data by creating a pivot table, and I looked at the relationship between sex and favorite color. I expect there to be a relationship here. Look at that column for pink, right? It's a 36-to-1 ratio for women over men. So I'm expecting there to be a pretty big chi-square statistic here. So if you want to follow along, either go into Excel and create this table yourself, or copy it down now. Once you're ready, we'll go on to the next slide. Let's start by doing this on our calculators. We'll begin by entering the data. We're used to entering data using the Stat menu and going to edit our lists. But we don't want to put these in lists because the relationship is stronger than just one list versus another list. We need something different. So instead, we're going to put our data into a matrix. You should see the matrix button over on the left. You'll need to hit second to get there. And the first thing you'll see is names and then math and then edit. We're going to focus on editing. And let's just stick with A. As long as you stick with matrix A, you'll be good to go. So the first thing it asks us for is the dimensions of this matrix. The first number here is the number of rows, and if you've got your data written down or you have it on your computer screen somewhere, you'll know that we've got 2 rows, and I'll push enter to move over to the next one. And the number of columns that we have 8 different choices for color, so this is going to be a 2x8 matrix, and I'll push enter. And now we just want to enter our data from left to right and top to bottom. In the first column we had 12. If you push enter, that moves over to the next one. Then 101, 38, 8, 36, 50, 25, 12. And it automatically goes back to the beginning for 23, 92, 26, 5, 1, 3, 10, 4. Once we have all our data entered, we'll quit and we'll go to the Stat menu. You'll find the chi-square test under, not surprisingly, tests. Chi-square is near the bottom, so if you go up, you'll get there faster. You see 2 things that look like chi-squared. One is a regular chi-squared test, and the other is the chi-squared goodness of fit test. We're not doing the goodness of fit test. Stick with the straight chi-square test. Now what your calculator asks you is, what matrix has the observed values? Well, they're in A. Next it says, what matrix has the expected values? You don't have to compute the expected values. What this is saying is, in the process of performing the chi-square test, it's going to put the expected values in B. So it's giving you an opportunity to change this to something else in case you've got some vital data in matrix B. But if you're not doing anything with matrices, you're probably good to just go down and select calculate. And notice that chi-square gets computed. We get a chi-square value of 65. That is enormous for 7 degrees of freedom. Remember, the chi-square should be centered at 7, so 65 is huge. And look at that p-value. It's something times 10 to the negative 11th. That's probably the smallest p that we've seen. Also, remember that your calculator put the expected values in matrix B. Let me show you how to get at those. If you go back into your matrix menu, under names, notice there's something here for A and there's something here for B. So B, option 2, now has the expected values, the expected counts for this test. You won't be able to see them all, but if you use your arrow, you can scroll over and write these guys down. All right? Now let's do the same thing, but with Excel. Here I've got my two-way table created using pivot table. Now it's important that what we're about to do does not play very well with the pivot table. So I know this kind of sucks, but what we're fixing to have to do is type out all these numbers again. There may be a way around this, but I don't know it. So I'm just going to type these guys in. You can use tab to move from one cell to the next in the same row. So 101, tab, 38, 8, 36, 50, 25, 12. And then the same thing for the males, 23, 92, 26, 5, 1, 3, 10, 4. Now it's going to be useful for us to have the total. So remember, we can get that using equals and then do sum of, and then you can click and drag over the numbers you want and push enter. And that's nice because we can drag it down and that gives us the sum of those. Now I also want the column totals, so this is going to be equal to the sum of the numbers above. And then I'll fill this across, all the way across, and now we have reproduced our two-way table, but in a way that we can actually get at these numbers more easily. So I'm going to come over here and label this as our observed values. Next, we're going to need our expected values. Excel doesn't do this for you. So remember, the expected value in the top left cell will be the sum of the first row times the sum of the first column divided by the total of the totals. So the expected count in that top left for black is the favorite color and female is the sex should be 22.13. Now sadly, if you just try to fill this across, it's not going to work. It's trying to divide by 0 because it's doing all of these computations relative to the position. So notice that it's trying to divide by the total of the totals. There's nothing in this cell. That's not working. So that's no good. You either need to do all these by hand, which sucks, or use the following little trick. If you put a $sign in front of one of the components of a cell, it means if you do the fill across or fill down, it won't change that part of it. So the total of the rows is over there in column J, and it's not changing out of column J. So I'm going to put a $sign in front of that J. The rows, or the sum of the columns, stays in row 11. It doesn't change out of row 11. So I'm going to put a $sign in front of the 11 there. And now the total of the totals is always in this cell, so I don't ever want the denominator to change from J11. So I'm going to put $signs in front of both the J and the 11. Now, when I fill across, everything works. And I can take that whole thing and fill it down. And now let's check our sums. Let's check that the sum of these two is actually 35. And it is. Success. And I'll fill that across and make sure. Notice that all of these numbers in the totals are the same. So now I've got the observed, I've got the expected, I'm ready to do the chi-square test. So over here, maybe in column L, I'll be ready to enter my chi-square. To get there, we're going to go under More Functions. We're going to go to Statistical, and we're doing a chi-square test. You see it here. First, it asks you for the actual range. So where are the actual values, the observed values? I'm going to highlight them. Make sure you do not include the totals. Leave the totals out of this. The expected range, we're going to do the same thing. There they are. And we hit OK. What's reported is the p-value. If you want the actual value of the chi-square statistic, you got to compute it yourself. I think a good way to do that is to create the components. Remember, the components of this chi-square statistic are the observed minus the expected, in parentheses, squared, divided by the expected. You can copy that down and copy that across. It's not affected by the the totals. And if you see down at the bottom of your screen right now, you should see the sum of those cells. It's 65.39. That's our chi-square statistic. You can also get it by doing sum, like we've done before, and just dragging over all the numbers you want to add up. So there's our value of chi-squared. There's our p-value, just like we got with our calculators. Just to remind you, let's see if I got it still here. It doesn't look like I do. We'll go back stat tests, chi-square test, observed, expected, calculate. Sure enough, there's our chi-square value, 65.3927, and their p-value of 1.25384 times 10 to the negative 11th. Good news. Here's the data that you're going to be using for your quiz questions. So go ahead and write these down or enter them into your calculator or whatever you want to do with them. Go ahead and pause the video long enough to get these copied down. So remember, to use chi-square, we need random samples taken independently, we need to control for confounding variables, we need sample sizes that are big enough, we need populations at least 10 times the sample sizes. Let's look at confounding variables. Here are students of all years, on campus and off campus, major, decided, and undecided. The chi-square statistic for this is 13.6. With 1 degree of freedom, that's huge. A p-value to 3 decimal places is 0. But if we break this down by underclassmen and upperclassmen, notice the difference. Underclassmen are much more likely to live on campus. Upperclassmen are much more likely to live off campus. Look at those chi-square statistics and look at those p-values. So do you really think that decided or undecided is related to living situation? With all groups lumped together, it looks like yes, very much. But once we control for number of years in college, upperclassmen versus underclassmen, those numbers look very ordinary. So once we control for class year, no. So to sum up, we talked about how to do a hypothesis test for a relationship between two categorical variables. We talked about framing the hypotheses in terms of variables or of parameters. We performed inference based on proportions and based on counts. We did a chi-square test on the accounts by creating a table of expected counts, comparing it to the observed counts and computing the chi-square statistic, and then evaluated chi-square using the chi-square distribution. We related the z and the chi-square for the 2 by 2 table. We saw how closely connected they were. We talked about the relative size of the chi-square statistic based on the sizes of the samples. We looked at the roles of explanatory and response in the chi-square test. We also talked about when it's appropriate to use the chi-square test. We looked at the role that sample size plays, and we computed some confidence intervals for 2 categorical variables and connected those back to our chi-square test. Additionally, we looked at computing the chi-square statistic. We did some calculations with this chi-square test, focusing on degrees of freedom and the density curve, that is the distribution. We checked some assumptions. We looked at computing chi-square with software, and we looked at the role that confounding variables can play.